Hi everyone and welcome back to the channel. In today's video, we'll be going through an FE exam thermodynamics review. Specifically, if you're studying for the FE mechanical or other disciplines exam, this review will be useful to you. You can see below I have the NCEES specification here. Specifically for the FE mechanical exam, you expect to see around 10 to 15 questions there on your mechanical exam. So this is an excellent place to focus your effort to maximize your chances of passing since it's such a large portion of the exam. You can see on the left-hand side, I have some numbers, and those numbers are the numbers of time that I'm going to be touching each of these sections here in the 8 problems that I'm going to be going through, and there's timestamps in the description, so you can jump to whatever problem or topic that you're looking to review. These 8 problems are taken from my software, FE Interactive, where their goal is to really explore some fundamental topics, like how do we use the property tables on the FE exam, the various kind of property diagrams like TS diagrams and PV diagrams, looking at ideal gases and ideal gas mixtures, and answering the question that a lot of students have, which is when do I use specific heat at constant pressure? When do I use specific heat at constant volume? We'll be exploring the first law for open and closed systems, looking at basic cycles and their performance parameters, the coefficient of performance, and the thermal efficiency, as well as those Carnot versions of those performance parameters. We'll review the vapor compression refrigeration cycle here, as well as the Rankine cycle, looking at isentropic efficiencies. We'll also do a problem dealing with the psychrometric chart here, as well as a combustion problem. This review will generally follow the following format where you see difficulty tags in the upper left. If the problem has a diagram, there'll be a diagram there, and there'll be a problem statement which states the question and answer choices. The FE exam is mostly multiple choice questions, so we try to focus on multiple choice questions here. And you'll also see a category section here where I'll highlight the relevant section that this question is trying to focus on. Now, how can you access all of these problems and try the review for yourself? You click on the first link in the description below, and it will take you to a screen just like this. You can click on the filter button here and then the thermodynamics section, and that'll show you all the problems that we're going to be going through in this review that you can try for yourself. And if you don't have a lot of time, you can definitely try these problems. And I have handwritten and typed solutions here that you can go ahead and view, save yourself some time. Now, I highly recommend you try these practice problems because you know the topics, right? All you need to do is practice and review some of these topics, and you will be ready to take the FE exam. So go ahead and try out those problems. Let's get into our first problem here. So this first problem is related to pure substances. Let's go ahead and get into it. For each of the thermodynamic states defined above, what is the phase description of each case? We're given 3 cases above with some properties, and we're asked to determine is it a compressed liquid, a saturated mixture, or a superheated vapor? Now, what's important about this problem is understanding fundamentally the idea of the state postulate. Now, the state postulate says that if you're given 2 independent intensive properties, then you fully define a thermodynamic state, like given temperature and specific volume. What you could do is find enthalpies, you can find internal energies, you can find entropies. Intensive just means independent of the mass. You can see that these properties have a per unit mass if they're specific properties, and temperatures and pressures are also intensive properties. Independence is important, and we'll discuss it more when we're looking at case 2. I wanted to give you guys some more context on the idea of property diagrams, and we're going to be using those property diagrams to go through each of these cases. So it's important to understand the context behind where those things came from. You can see on the right-hand side, I have a pressure versus temperature axis, and I kind of clearly identified the solid, liquid, and gas regions. I also labeled that the kind of barrier between liquid and gas is called the vaporization line. Now, this kind of diagram, this behavior is seen in all pure substances, like let's say water. If we have water at standard atmospheric pressure and a temperature which is below 0 degrees Celsius and we begin heating, we transition from a solid to a liquid and then from a liquid to a gas. But for a substance like dry ice, what we see is that if we expose it to standard pressure and begin heating, we go straight from solid to gas. So you can see that though this diagram is true, what happens is a scaling on that axis depending on what kind of pressure that we're looking at. If we increase the pressure on that dry ice sufficiently, what we could see is that, we start off as a solid, we go to a liquid and then a gas, right? So it's all about what kind of pressure that you're at. Now, you see that I only have one line labeled here, and that's because the vaporization line is the most important to us. Engineers like to work with substances which are able to transfer energy across distances, like liquids and gases, because they can flow. So that's why we use liquids and gases in steam power plants. We'll use them in refrigeration cycles. We'll use them in jet engines because they're able to transfer energy easily. So what we did, because liquids and gases are most important to us, is we isolated that barrier between liquid and gas. And if I go ahead and draw a diagram like a temperature versus specific volume diagram, which we're going to use to solve this case 1, what we did was we isolated the vaporization line, or the barrier between liquid and gas. So when you can no longer see the difference between a liquid and gas, that's referred to as the critical point. And the critical point on the dome is this upper point right here. This entire dome is just the isolated vaporization line that separates the compressed liquid region and the vapor region, the superheated vapor region. And something between means that you're between a liquid and a vapor, and that's where the idea of quality comes from. So I just wanted to mention this so that we kind of understand what that dome represents. It's just the isolated vaporization line. And let's go ahead and use this diagram and give some more context on it to be able to solve that case 1. Okay, so usually to identify the state, what I like to do is draw a property diagram. And it's a good visual way to kind of identify the state. You draw a temperature, and because we're given a specific volume in this case, I'm going to put specific volume on the x-axis. I'm going to draw my saturation dome, and at a given temperature of 180 degrees C, there's only one saturation pressure, which is Psat. Okay, so now that we have the general form of our property diagram, what we're going to do is, since we're given specific volume, we're going to compare our given specific volume to the specific volumes at these extremities here, where at the left side of the dome we have VF, which is the specific volume of a saturated liquid, and on the right side of the dome we have VG, which is the specific volume of a saturated vapor. Now, depending on where we are with our given specific volume, we could be inside of the dome, which would conclude that we're a saturated mixture. If we're greater than VG, we'd have a superheated vapor. And if we're less than VF, we have a compressed liquid. Okay, so what we're going to do is at 180 degrees C, see what VF and VG is in our property tables. So in the FE exam reference, in the thermodynamics section, in the steam table section, what we're going to do here is we're going to look at 180 degrees Celsius. And what we could see is that VF at 180 degrees Celsius is 1.127 times 10 to the minus 3. VG is 0.194. So we have VF is 1.127 times 10 to the minus 3. VG is 0.194. That's cubic meters per kilogram. And our given specific volume, the V1, is 1.25 times 10 to the minus 3. Now our V1 is between VF and VG. That 1.25 is a little bit bigger than the VF value that we're given. What that means is that if we draw our V1, we'd have intersection within the dome. And if we draw that intersection point, it would be here. So because we intersect within our saturation dome, we have a saturated mixture. So the first one is a saturated mixture. Now what that means is that we could immediately eliminate choice A, and we could eliminate choice D as well. We know we're either choice B or C. Let's move on to case 2 so that we could fix our choice. Now for case 2, we're given a temperature and a pressure. if we draw our property diagram here, I always put temperature on the y-axis because it's the least amount of things to remember in terms of our direction of lines of constant pressures. Now for lines of constant pressures, I know they slope upwards. If we have like a PV diagram, for instance, you additionally have to remember that lines of constant temperature are actually backwards. They slope downwards. I usually stick to one of these diagrams so that I only have to remember one of them. And it's usually that temperature diagram. So at 150 degrees C, which is our temperature that we're given, we will have a saturation pressure. And we have a given pressure, P2, that we're not sure how it compares to the saturation pressure. So that's the information that we need in order to fix our thermodynamic state. If we go at 115 degrees C, what I'm seeing is that the pressure is 0.169 MPa or approximately 170 kPa. Psat is 170 kPa, and our given pressure, if we draw our line of constant pressure, which increases in this kind of direction, our P2 value is 175 kPa. We kind of picture that intersection where it's going to occur. The intersection will occur here in our compressed liquid region. Okay, so this is a very good visual way to really understand what your state is. We see we're a compressed liquid here. If we go up to our choices, what that means is that we're definitely going to pick choice B. That's the correct answer. Okay, in terms of understanding the idea of independent, which I said we're going to discuss further in case 2, if you're given a temperature and a pressure, they're not always independent. For instance, if you're told that you are a saturated mixture and you're given a temperature, a saturation temperature, that means there's only one pressure you can be at within the dome. And for that given pressure, there's many different places where you could identify that property to satisfy the temperature and saturation pressure. So we're not fully fixed if we're within the saturation dome. We need another intensive property like specific volume. We need an enthalpy. We need a quality, which is the percent of the mixture, which is vapor. So that's an important idea to understand that if you're a saturated mixture, temperature and pressure are not independent. Okay, let's move on to case 3. Now for case 3, we're given a pressure, P3, which is 200 kPa. And we're also given an enthalpy, which is 2,800 kilojoules per kilogram. Now, again, what we're going to do here is draw our property diagram. We're going to go with a temperature versus enthalpy diagram here because we're given that enthalpy. Draw our saturation dome and draw our saturation pressure line, our Psat, which we're going to assume is 200 kPa. Now, we're not sure what Tsat is, but we can go ahead into our property diagram, into our property tables, and find out what that is. And our general strategy here is to compare this enthalpy that we're given to an HF and an HG value at our given saturation pressure. So if we go ahead into our property tables again, what I'm seeing is that at a pressure equal to 200 kPa, which is somewhere between these two pressures of 198 and 232, I'd have some enthalpy properties which I could extract and compare to my enthalpy that I was given. I'm going to screenshot this table here. That's this stuff right here. And we're going to paste it down here. Okay, so I know that for my given pressure, which is 200 kPa, I'm somewhere between these values. If I wanted to do this problem completely, what I do is I'd interpolate between the HF and HG values. This is the H column here, HF, and this is HG. I'd interpolate between these values here at that given pressure. But what I know is that 200 kPa is much closer to 198 kPa compared to 232 kPa. So I'm going to assume my HF is around 504 and my HG is around 2707. And what my H that I'm given is, my H3 is 2800 kilojoules per kilogram. And I can see that that's greater than my HG value. Even if we weren't completely accurate in our interpolation, the most that HG could be is this 2713 value. So I definitely know that for sure I am above that H value. I'm greater than HG. So this is my H3 here. And I'd have intersection to the right of the saturation dome, which is the superheated vapor region. Choice B. In this problem here, we have an ideal gas, and it's said to be helium here. It's contained in a frictionless piston cylinder device. Initially, the gas is at a temperature, let's call that initial state 1, and it's at a temperature equal to 27 degrees Celsius, and a pressure, P1, equal to 200 kilopascals. It undergoes a constant pressure heating process, so that means the pressure at state point 1 is the same thing as the pressure at state point 2, and it expands to a final volume, that's V2, equal to 2 cubic meters. The mass of the helium in the cylinder, mass is equal to half a kilogram here. The total heat transfer into the system during this process, Q, is the unknown. So we kind of have a piston cylinder device here. I'm drawing the cylinder with the piston on top. And I'm going to go ahead and, if we kind of think about what's going on in this problem, we have the helium, which is contained inside of the cylinder. It has some mass inside of that cylinder, and as we heat, the actual piston is rising, right? It's increasing its volume to an increased state, and that's that V2 right there. We think about the process that's going on here. The process that's occurring, if we draw it on a PV diagram, and we draw that isolated vaporization line separating the compressed liquid region and the superheated vapor region, call that the gas region here. We can draw on the lines of constant temperature here, which are pretty much these kind of downward stair steps here. I know that we are an ideal gas here, so that means that we're going to be on the right side of the saturation dome. And I'm going to be in this region. And for a constant pressure process to occur, I know that I'm going to be moving horizontally. And because we're going through an expansion, we know that the specific volume is going to be increasing, right? We're increasing the volume, so that means that we're increasing the specific volume. Remember, specific volume is just volume per unit mass, right? The mass is not changing in the system. So if we increase the volume, we're just increasing the specific volume going from state point 1 to state point 2. Okay, so we kind of understand the process that's going on here. So I'm going to check that off, and we're looking for heat transfer. When we're talking about heat transfer, the first thing that pops in my mind is the first law of thermodynamics, which says that heat transfer minus work is the change in the energy of the system. And there's a different first law depending on if you're looking at a closed system or an open system, right? And what's the important distinction between them is if we kind of draw our system boundary here, which is this dotted line that I'm drawing, the walls of my boundary here are pretty much the walls of the cylinder and the top side of that piston. So that's forming my boundary here. And you can see that mass is never crossing the boundary. When mass crosses the boundary, we consider that an open system. When mass doesn't cross the boundary, we consider it a closed system, right? And if we have a closed system, the first law takes this form that we have changes in internal energy, changes in kinetic energy, and changes in potential energy that replace that delta E term here. And we still have on the left side heat transfer minus work. Note that the heat transfer is what we're looking for. And if we think about some other terms that we can quickly get rid of, there is no speeds mentioned in this problem, so the change in kinetic energy is just going to be 0 here. And there's no heights or dimensions given in this problem, so we're going to neglect potential energy changes. So our first law kind of just becomes heat transfer minus work is equal to the change in the internal energy of the system. And if we think about some of the components of the first law, I'm going to check off this This box up here, we discussed the idea of system boundary, right? And the distinction between open and closed system. If we look at some of those components contained in the first law here, we have heat transfer, that's what we're looking for. And then we have work, right? If we focus in on that work term, fundamentally work can always have two components. There's other forms of work. That's like work from electrical resistances, work from mixing devices, or just other kind of inputted work. And then there's boundary work. Now, boundary work is a special kind of work here, and it's defined as the integral of PdV. It's the work attributed to expanding or contracting a boundary. And you can see that in this case, that's very applicable to us because as that piston here is rising up, you can see that our boundary is expanding. We expect to have some boundary work in this case. Now, for our case in particular, we have a constant pressure process. We can take that pressure out of the integration and we just have the integral of dV, which is just P V2 minus V1 or P delta V. So we understand how we can compute the boundary work in this case. And our first law basically reduces to heat transfer is equal to the change in the internal energy plus P delta V. Now, we're going to come back to computing that heat transfer, but I want to show you guys in the reference manual where you could find some of this important information. And you can see I have it highlighted here on page 147. So let's go ahead and take a look at that. On page 147 of the FE reference manual, you can see that we have mention of the first law of thermodynamics, and specifically we're working with closed system here. So this is what I wrote out for the first law of thermodynamics. We neglected kinetic and potential energy changes, and we were kind of left discussing that work term. Now we had a constant pressure process here, so the boundary work took this form. You can see in the reference manual, they have the work per unit mass, which is why the volume we had P delta V, they have P times delta specific volume. That's because if you take the volume divided by the mass, you get the specific volume. So that makes sense. Now, if you have a constant volume process, the boundary work is equal to zero. That makes sense, right? You're not expanding or contracting the boundary. It's staying completely still, so you expect to have a zero value boundary work. And if you think about it mathematically, if you have the integral of delta V, a change in volume, you have no change of volume, so it makes sense that the boundary work will be zero for that case. Another important case is when you have a polytropic process. That's when the pressure and volume have a relationship between them. That pressure times volume raised to the polytropic exponent is equal to a constant value, and that's true for the entire process. And if the polytropic exponent is not 1, this is how we compute the work per unit mass, the boundary work per unit mass. And if it is equal to 1, which you can see is this case right here, that's basically having a constant temperature process for an ideal case. Or if they specify that n is equal to 1, then you would use this relationship right here to find the boundary work. And there's also another special case where you have an isentropic process where the polytropic exponent is the ratio of specific heats. That's called Laplace's coefficient. And you can see you can also compute the boundary work using this equation here. So that's all about work. And let's get back to discussing the kind of form that we settled on here for computing the heat transfer, which is that it's equal to the change in internal energy plus the product of pressure times the change in volume. Now, this set of terms here actually is the definition of another thermodynamic property. The change in internal energy plus the product of pressure times the change in volume is actually the change in the enthalpy. So we can go ahead and look at that in the reference manual, but fundamentally what we're looking for is to compute that change in enthalpy. If you're computing enthalpy changes, what you're going to be using is, for an ideal gas, you use mCp delta T. If you're looking at internal energy changes, you use mCv delta T. So a lot of people struggle with when to use Cp, when to use Cv. If you have an enthalpy change, you're going to be using Cp. If you have an internal energy change that you're trying to find, you're going to be using Cv. So we kind of successfully went through the discussion here on the enthalpy definition. And really all we need to do to be able to solve this problem is we know what the mass is. We can find Cp from the tables, and the temperature at state point 2 is the only thing that's unknown for us. And we can find that using the ideal gas equation, right? Or the ideal gas law here. If we have, if we think about some of the knowns that we have the volume at state point 2. We just write down the ideal gas law here. PV is equal to mRT, and we know that we're looking for the temperature at state point 2. So T2 is equal to pressure at state point 2, volume at state point 2 divided by the mass multiplied by the gas constant. We know the pressure because the pressure at state point 1 and state point 2 are the same. We know the volume, it was given. We know the mass, and we can go ahead and find the gas constant right now. Let's just plug in everything for now. What we have the pressure at state point 2 is 200 kilopascals. The volume at state point 2 is 2 cubic meters. The mass is half a kilogram. And the gas constant R, if we quickly check inside the FE reference manual here, for helium, I'm going to click on I know it's in the final part of the thermodynamics section. I'm going to click on the fluid section and scroll up a little bit. And we're going to get to these properties here for, let's see, for gases here at room temperature. And, this is the kind of the only option we had. Ideally, we would have what the gas constant is at a specific temperature, right? And the CP at a specific temperature, but, all we have is a room temperature properties here. So this is how we're going to be kind of approximating the solution. And if you see here, we have helium. The CP is 5.19 kilojoules per kilogram Kelvin. So we're going to note that down, as well as the gas constant R. That's 2.0769. Let's go ahead and log those values here. R is 2.0769 kilojoules per kilogram Kelvin. And CP is equal to 5.19 kilojoules per kilogram Kelvin. Let's plug in the R here, 2.0769. And if we look at some of the units here, reduce this. Look at some of the units here. We have the 200 kilopascals, that's measured in kPa. kPa, another way to write that is kilonewton per meter squared. And if we multiply top and bottom by meter, what we could get is a kilojoule. A kilonewton meter is a kilojoule per cubic meter. If we go ahead and write down what that volume is measured in, it's measured in cubic meters. So those units are going to cancel out. We have the mass measured in kilograms, and we know that R, the gas constant, is kilojoule per kilogram Kelvin. The Kelvin crosses out, the kilojoules cross out. We're left with Kelvin, which is exactly what we want. We go ahead and quickly compute this. It's just 800 divided by 2.0769. We get that T2 is equal to 385.19 Kelvin. And we were given T1 of 27 degrees Celsius. Remember, we have to convert that Celsius into Kelvin. 27 plus 273.15 is 300.15. Okay, so technically we could, if you're looking at a delta temperature, all you need to do is be able to have them in the same units. We could have used a delta T in Celsius or a delta T in Kelvin is exactly the same. But, we already have this answer in Kelvin, so we're going to just convert our input, our T1 value to Kelvin as well. Okay, let's go ahead and plug into what we have to do here. We have the mass, which is half a kilogram. We have the CP value, which is 5.19, and that's kilojoules per kilogram Kelvin. And we have what the delta T is. That's just 385.19, that's T2, minus what the temperature is at state point 1, 300.15. Both of those measured in Kelvin. That the heat transfer that occurs during this process is 220, and that should be measured in kilojoules. I'm seeing that's answer choice C.
In this problem here, we have a house that's heated using a heat pump. Heat is lost from the house at a rate of 23,000 kilojoules per hour. That is a power, right? It's an energy or joules per unit time or hours. The house is maintained at a temperature, the house temperature is equal to 30 degrees Celsius, while the outside air is equal to -5 degrees Celsius, the minimum power required by the heat pump is most nearly. Okay, so the first thing I'd like to do for this problem, which is really focused on heat pump cycles and in general some energy transfers and the laws of thermodynamics, is to go over some points that I have in the upper right of the screen there. And I think these points here are really fundamental to understanding these problems and give a good basis for some of the cycle problems that we're going to do later. So let's get right into it. We're going to start off here with a refrigerator or a heat pump, which has the same basic kind of cycle structure. The cycle is what's in the center, and essentially, let's talk through the case of a refrigerator. We take the kind of low temperature source, that's the source that's associated with the inside of the refrigerator, right? We want to keep all of that food cool. So we suck heat out of all of that kind of low temperature source, all of the food in the refrigerator, and we transfer it to a high temperature sink. That's the outside of your refrigerator. And we do that by using a compressor. And we input some work into that compressor so that we can transfer heat from a low temperature source to a high temperature sink. Right, remember, heat naturally flows from high to low temperatures, but if we input work, we can achieve the opposite. Now, how does this work in practice? Is that we have special fluids that we use that can evaporate at low temperatures, right? That's like the fluids that are inside of refrigerators, like R134A, right? They have tables for those in the FE reference manual. We'll take that fluid, and when we expose it to that cold food inside of the refrigerator, the cold inside of the refrigerator, we're able to evaporate that fluid, and it takes energy to evaporate that fluid. That energy is essentially being sucked out of the food inside of your refrigerator. We'll take that fluid that's now in a gaseous state and we'll input work into a compressor to compress it and heat it up. It'll be heated up so much that it's hotter than the outside, the surroundings, that we can essentially achieve heat transfer with the outside of the refrigerator, right? The kind of ambient temperature, because that gas will be so hot it can reject the heat to a high temperature sink. Now, refrigerators and heat pumps, they're very similar in their structure. They work exactly the same way. And there is a performance parameter associated with a refrigerator. There's also one associated with a heat pump. That performance parameter, just like the one associated with the heat engine, has a kind of standard definition. That standard definition is the desired output. What are we looking for our device to do? What is the desired output of our device? And what is required for us to input? So this is the standard definition of efficiency, which is essentially our performance parameter. A performance parameter specifically for the refrigerator is the coefficient of performance, the COP for a refrigerator. That's what this little subscript here means. And for a heat pump, it is this. Now, the desired output for a refrigerator is we want to suck as much heat out from whatever's inside of the refrigerator and keep it cool. We want to keep the cold stuff cool. So our desired output is we want to maximize that QL term. What about for a heat pump? For a heat pump, we want to reject as much heat as possible to the high temperature sink. That's the QH, right? We want to keep the hot stuff hot. So that is QH here. So you can see they differ in the numerator, but their input is exactly the same. Our required input is work input into a compressor, work in. So this is essentially what the COP are and the COP for a heat pump are, and you can find them in page 149 of the reference manual, and we'll look at that a little bit later. But I want to keep going with this idea here. If I can find my mouse. Okay, I found it. Let's move this over a little bit because additionally, with this idea of COP, there is a maximum possible COP that we can achieve, and that's the Carnot COP, right? And essentially, it comes from the idea that the temperature ratio is equivalent to the heat ratio. You can see that we can also write the work input as the difference between QH and QL. What's coming in, that's the work input here, and the QL, and what's going out, the QH, so that we can write this relationship essentially applying the first law of thermodynamics to that cycle, right? Note that the first law of thermodynamics states that heat transfer minus work is the change in energy, and for a cycle, there is no change in energy. We begin and end at the same thermodynamic state such that the heat is equal to the work. Right? Once we do that and account for the signs, we get this equation right here that we can substitute into our denominator. QL is equal to that. Remember that work input is just the difference between QL, QH and QL. QH minus QL, and we have a QH here. If we divide by the numerator in both of these cases, what we get is, and for the Carnot efficiency, we set the heat ratio equal to the temperature ratio. So for the case of a refrigerator, we have TH over TL minus 1. And for the case of a heat pump, we have 1 over 1 minus TL over TH. And this is the kind of COP or a heat pump associated with the Carnot cycle, which is the maximum possible COP that we can get. And this is relevant for us in this problem because we're going to be using this idea to compute the minimum work input, right? To get the maximum COP, the most efficient COP, the most efficient heat pump, we're going to be inputting the minimum amount of work, right? Inputting the minimum amount of work such that we maximize the COP of the heat pump. Okay, so I know that was a lot of words to essentially explain the basics of a refrigerator and some of those performance parameters and the idea of that temperature ratio and the Carnot cycle. But with this, we would be able to solve this problem. I'm going to quickly talk through the idea of a heat pump. For a heat pump, all we're doing is we're taking energy from a low temperature source. Like for this problem, we have a low temperature source at -5 degrees C. We're going to take that low temperature source and transfer heat from that low temperature source to evaporate a working fluid. We're going to compress that working fluid, which is now in a gaseous state, to transfer heat inside of the house. Right? We're going to heat that fluid up at the low temperature source so much that we're able to transfer heat to the high temperature sink, which is the inside of the house that's maintained at 30 degrees Celsius. And the heat is lost from the house at a rate of 23,000 kilojoules per hour. That's essentially the heat that we must supply into the house. That QH, or Q dot H for us, is 23,000 kilojoules per hour if I change these to dots here. Okay, so the COP for a heat pump, is equal to the desired output, which is the Q dot H, over the required input. That's the kind of minimum work input that we have. And for the Carnot case, we know that that's equal to this equation right here. Okay, so we know the temperature of our low temperature source and our high temperature sink, so we can plug in right here 1 divided by 1 minus the temperature of our low temperature source, and these must be in Kelvin here, which is really important. -5 plus 273.15 is the temperature of our low temperature source right here, converted to Kelvin, and the temperature of our high temperature sink is 30 plus 273.15, such that the coefficient of performance for a heat pump or the most efficient cycle, which would require the minimum work input and transfer the most amount of heat, is 273.15 minus 5 divided by 30 plus 273.15. 1 minus that answer, 1 over that. Okay, so this is 8.66. Now, we found the coefficient of performance for a Carnot cycle, and we know what the work input, we know what the heat transfer to the high temperature source, the rejected heat, is. So we can use that to find the minimum work input. All we do is we rearrange that equation, taking the ratio of Q dot H divided by COP for a heat pump in the Carnot case, and we can find that minimum work input. So we know that the heat transfer, the heat rejected to that high temperature source is 23,000 kilojoules per hour. Kilojoules per hour divided by the COP for a heat pump, 8.66. 23,000 divided by that is 2655. That is kilojoules per hour. And to convert that into watts here, all we do is, let's go ahead and work out those units here. In 1 kilojoule, there is 1,000 joules. And there in 1 hour, there's 3,600 seconds. So that'll give us a joule per second or a watt. If I multiply this by 10 to the third and divide by 3,600, what I get is 737 watts. That looks like the solution is choice C. Okay, so you can see I had two schematics here. I also want to discuss the idea of a heat engine, right? Because it's important to review that idea. And, associated with the refrigerator and the heat pump is, the vapor compression refrigeration cycle, which we're going to do an example on a little bit later. But for the heat engine, there's so many examples, right? There's the Otto, the diesel, the Rankine, the Brayton cycle, which are all based off of this kind of basic idea of this schematic that I'm going to draw for you guys, which is we have a cycle in the center. We take heat from a high temperature source and input it into our cycle, and we're able to produce work output. But when we produce workout, we have to reject heat to a low temperature sink. And that's why on engines, for instance, you see fins, right? As they're producing work, they're also producing heat. And we have to transfer that heat somewhere. So we reject it to a low temperature sink. Okay, so that's the basic idea of a heat engine. And the performance parameter associated with the heat engine is this eta term. And the desired output for our heat engine is to maximize that amount of work output. What's the required input? The required input is the heat here, the heat from the high temperature source. Okay, and for the Carnot, you can see that the work output here is essentially equal to the difference between QH and QL. QH minus QL divided by, this was QH here. So you can see that the Carnot efficiency, right, which would be equal to the ratio of the heat ratio is essentially equal to the temperature ratio. If we go ahead and divide by QH, you can see that the Carnot efficiency, eta sub C, is equal to 1 minus TL over TH. I'm going to quickly show you guys inside of the reference manual where all these formulas can be found, and the section on this kind of topic is found here. So basic cycles here on page 149 of the reference, you can see that they explain the idea of efficiency, and there's no desired output over required input, but that's kind of the logical argument for how you get to some of these formulas here. That's the eta. The Carnot cycle represents the most efficient heat engine, and it comes from that idea of the temperature ratio being equivalent to that heat ratio. And there's some for a COP for a heat pump or refrigerators, and air conditioners. And you can see that there's also the Carnot efficiency associated with those. Okay, let's move on to the next problem. In this problem here, we're really going to be focused on pure substances, performance of components, and the vapor compression refrigeration cycle here. So what we have is R134A, and it's undergoing a refrigeration cycle with the evaporator exit given at some pressure and some enthalpy. Then we have the compressor exit given pressure and enthalpy, and we know it's a saturated liquid at the condenser exit.
and we're looking for the coefficient of performance here. So you can see some things on the upper right that I really think are fundamental to understanding this problem. So we're going to be going through those as we solve the problem here. So the first thing that we're going to do is review what is the idea of the vapor compression refrigeration cycle. Now, essentially, this cycle operates at between two pressure bounds here. These are lines of constant pressure that I'm drawing in here. And what we have is four components. The first being the evaporator, the next being the compressor. The component above is the condenser. And then this component over here is called a throttle valve or an expansion valve. And essentially, what's going on is we have a working fluid in the system. That working fluid takes heat from the low temperature source. So this is kind of the QL here. Take heat from that low temperature source and use that energy to evaporate. Once it's fully evaporated at state point 1, we input it into the compressor where we increase its temperature, we increase its pressure to conclude there at state point 2. Now, that working fluid is super hot and it's able to transfer heat to the high temperature source here. That's the ambient environment. So we reject that heat and we kind of cool down here, lower our temperature, traveling along this constant pressure line to state point 3, where we are a saturated liquid. And that's because we are a saturated liquid at the condenser exit here. This is the condenser. And then we go through an isentropic process, constant enthalpy process, where we end off at state point 4 here. And we return back to state point 1 to complete our cycle. So this is the idea here of the vapor compression refrigeration cycle. We transfer heat from a low temperature source, that's the inside of your refrigerator, to a high temperature sink, and we accomplish that heat transfer by inputting work into a compressor to heat up the working fluid so that we can perform that heat transfer that we're looking for. Remember fundamentally that the coefficient of performance for a refrigerator is just the desired output over the required input. We want to take as much heat as we can out of the cold stuff. We want to keep the cold stuff cold. So we want to maximize that QL, and the required input is the work input to the compressor. Now, we can do this in terms of, energies, or we could do it in terms of energy per unit masses. And we could write down some of these terms in terms of the enthalpy changes. So the heat transfer from the low temperature source is essentially H1 minus H4. That's just the bounds here around the evaporator. And 1 will have more energy because it is a vapor form. So I know that that is going to be the first term here. The required input is just going to be H2 minus H1. And that's just the bounds around the compressor, right? Okay, so this is what we need here. And if we think about some of the knowns and some of the unknowns in this problem, let's go ahead and label what our givens are. So the evaporator exit is state point 1. At state point 1, we're given a pressure of 17.4 psia, and we're also given an enthalpy at state point 1. BTU per pound mass, the energy per unit mass that was given, is 101.89. See, this is an English system problem here. At the compressor exit here, the compressor exit is going to be state point 2. The pressure at state point 2, you can see the large increase in pressure, 101.53 psia, and the enthalpy at state point 2 is given as 117.58 BTU per pound mass. And we know that at the exit of the condenser, at the condenser exit here, we have a saturated liquid. So at state point 3, we know we have a saturated liquid. That means we have a zero value quality. The percent of the mixture, which is vapor, is 0%. We have a saturated liquid at state point 3, and understanding the vapor compression refrigeration cycle, we know that the pressure at state point 2 and the pressure at state point 3 is exactly the same, right? Constant pressure process occurs in the condenser. So we know P3 equal to P2.
is 101.53 psia. Okay, if we're able to find the coefficient of performance here, then we solve the problem. We know the enthalpy at state point 1, it was given. The enthalpy at state point 2, we also know. The only thing that's unknown is the enthalpy at state point 4, and we know that in the throttle, a constant enthalpy process occurs, so H3 is equal to H4. Now, we know some things about state point 3. We know it's a saturated liquid, and we understand its pressure. So we know the quality is 0, and that's the saturation pressure we have. So we'd be able to find the enthalpy for state point 3, which is the same thing as enthalpy at state point 4. So to summarize what we're looking for in this table, at P3, which is just P2, which is 101.53 psia, we want to find the enthalpy of a saturated liquid. So let's go inside of the tables. We're going to find that enthalpy of a saturated liquid, because that's going to be equal to the enthalpy of state point 3, which is the same thing as the enthalpy of state point 4. Let's see if we can find that value. It looks like, okay, I also had up a TS diagram here if you wanted to see a cleaner schematic and, kind of emphasize that the coefficient of performance we're finding is exactly what's in the reference manual. It's the desired output. The desired output is just the difference between H1 and H4. That's the heat in from the low temperature source, and the required input. What's the required input is to work into that compressor. You can see that term right there is the difference between H2 and H1, right? Okay, so let's go ahead and head into the R134A tables. Okay, so we have R134A tables, saturated liquid and saturated vapor, and we understand that the pressure that we're given is 101.53 psia. Now, we don't have that pressure in particular, so we're going to have to perform some interpolation, but it is pretty close to this kind of pressure that's shown right here, the saturation pressure. So we could just kind of directly take that off, but for completeness, I'm going to go ahead and interpolate for you guys. So I'm going to mark off the pressure bounds between the pressure bounds that contain 101.53 psia. So it's somewhere between this value and this value. And I know that I'm looking for the enthalpy of a saturated liquid. Looks like this column right here, the 38 and the 39 here. Yeah, so definitely if I was taking my FE exam, I would just go ahead and grab this value, because 101.54 is so close to this value. We could just grab that 38 and we'd probably be okay. We'd definitely be okay, because look at the delta between these two values. It's only like 1 BTU per pound mass, so 1 or 2. But let's go ahead and grab the values and we'll go ahead and interpolate. So if you think about the process of interpolation, we essentially know what the pressure is. The pressure is going to be our input. The enthalpy is our output. What is the pressure that we have? Well, we have a pressure somewhere over here of 101.53, and that's the pressure that we're looking for. And we know the data that surrounds this pressure, right? We have a pressure value equal to pressure of, 101.39, pressure of 101.39, and then a pressure of 109.93, and that is measured in psia. And then additionally, we have an enthalpy of a saturated liquid, which corresponds to 38.195, and 39.913. Okay, so given a pressure value of 101.53, we want to be able to find our enthalpy, which we can easily do on the calculator. I'm going to show you guys how to do that right now. Actually, let's click on data, and we're going to input our list data here, which is 101.39. This is essentially going to be our X values here, 109.93. Okay, so we have our X values and we need the Y values, or the enthalpies associated with that.
195. And then 39.913. All right, so we have all our data. We're going to quit out of that, and then we're going to click second data, and we're going to go down to linear regression. So we're essentially performing a linear regression on the pressure and enthalpy, pressure being the x-axis here. We're going to click through all of these options here. I want to use my x data as what's in my first list, my y data as what's in my second list, and frequency is just set to 1. Going to calculate that linear regression here, and we have a and b values. A is essentially your slope, b is your y-intercept, and we know the equation is going to take on the form y equal to mx plus b. So I know that my x value is just 101.53. That's my pressure. Multiply that by a. You see I'm accessing my stored variables here, mx plus b, and that's just stored right here, my y-intercept value. So I get a value that is pretty close to that 38.195, which is what I was looking for, 38.22. 38.22 BTU per pound mass. If I go ahead and plug that in into my equation right here, the enthalpy at state point 1, that was equal to 101.89. Enthalpy at state point 4 is 38.22. Divide that by the enthalpy at state point 2, 117.58 minus 101.89 here. If we plug that into the calculator here, 4.06, that looks like to be closest to choice A. So that's the solution here. If you want to see more calculator tips, you can refer to the video that I'm going to put on screen right here. Okay, let's move on to the next problem. In this problem, we have a steam power plant. That steam power plant is operating with water as the working fluid, so we're going to be working with water in this problem. The boiler delivers steam at 475 degrees and 5.5 megapascals, while the turbine exhausts at 60 degrees C and it's a saturated vapor. The mass flow rate, m dot, is equal to 42 kilograms per second, and the pump isentropic efficiency, eta sub p, is equal to 83%. And what we're asked for is, what is the pump power, W dot, for that pump? Okay, so let's quickly review the steam power plant cycle, which is the Rankine cycle. Rankine. And in general, the Rankine cycle operates between two pressures, one high pressure here and one low pressure here. Remember, those lines of pressures are like stair steps on a temperature. When the vertical axis is temperature, the pressure is kind of like a stair step. So let's start off here at state point 1. And at state point 1, we essentially have a saturated liquid. You can see that we're touching the left side of the saturation dome. And what we're going to do is increase the pressure of the fluid, and as we increase the pressure, we're increasing the temperature as well. To end off at state point 2, where we have a high pressure liquid, and that pressure increase is occurring inside of a pump where we have to input some work in, right? A pump is a work input device. We input some work into it, and the output is an increase in pressure of that fluid. We'll go ahead into the next system here, which is a boiler. And the boiler basically increases the temperature of the water. It increases the temperature of the water at a constant pressure until it hits state point 3. And the boiler requires some heat input from a high temperature source. So we input heat into the boiler, and as we input heat energy into that boiler, it increases the temperature of the fluid until it becomes a superheated vapor. The next thing that we're going to enter into at state point 3, which is the exit of the boiler, is the turbine here. And the turbine produces work out. It produces work out here, and
that occurs via expansion, you can see that all these lines, the work input and output that I'm drawing, are isentropic, constant entropy. That's why they're fully vertical here. And we return back to state point 1. And this device here is a condenser going from a saturated saturated vapor here at state point 4 all the way down to a saturated liquid. Now let's label some of the inputs that were given here. So it says the steam power plant operates with water as the working fluid. The boiler delivers steam at 475 degrees C and 5.5 megapascals. So that means that the temperature at state point 3, which is what the boiler is delivering steam to the turbine, 475 degrees Celsius, and a pressure. So we know that the high pressure of the system is at 5.5 megapascals, while the turbine exhaust, the temperature of the exhaust of the turbine, or T4, is equal to 60 degrees C, and we know that it is a saturated vapor. Another way to say saturated vapor is that the quality at state point 4 is equal to 1. The percent of the mixture, which is vapor, is 100%. So we have a quality of 1 at state point 4. And that's essentially what we have here in our givens. And our goal is to find the pump power. Now, you can see that I drew all vertical lines, but this would represent the ideal Rankine cycle. The non-ideal Rankine cycle would actually have a kind of slope here because we would increase the entropy, right? So this would be like the 2 actual. This will be the actual state associated with 2. And for state point 3, which is an expansion device, we would actually slope to the right here, and this would be for actual. So this would be the non-ideal kind of Rankine cycle before we drew the ideal Rankine cycle. And to go from 1 to 2A, or to go from 3 to 4A, we essentially use the idea of the isentropic efficiency. And the isentropic efficiency is this term eta, and there is a distinct isentropic efficiency for a work input device like a pump versus the isentropic efficiency for a work output device like a turbine. Now, always think in your mind that the isentropic efficiency is always less than 100%. And you're thinking about the ideal machine versus the actual machine. So for a pump, if you think a work input device, what would be the best possible work input device? The best possible work input device would be the one that I need to input the minimum amount of power, right? So technically, the work input device that I need to input the minimum amount of power is W sub S, and that would be the best possible kind of work input device or pump. I input the minimum amount of power. It's the ratio of the minimum amount of power that I can input. That's the ideal divided by the actual. Right? The actual pump will require a little bit more energy because it's not 100% efficient. Now, what about for the turbine? The ideal turbine will produce the most amount of energy. So actually, the ideal case actually goes in the denominator for that turbine because we want this ratio to be less than 1. So we want the biggest value in the denominator, the ideal case in the denominator, and the actual case, the actual turbine produces less, right? It's going to produce less power than the ideal turbine. So you can see the distinction between a work input device or a pump on the left-hand side and a work output device like a turbine on the right-hand side. They're reciprocals, which is a little bit tricky, but thinking that the pump or the turbine, the isentropic efficiency is always less than 1, it's pretty clear to come up with these formulas, right? And they're in the reference manual as well. So in this problem, what we're really looking for is this work input, right? And the thing about computing the work input is that it's super easy to compute it in the isentropic case, and the isentropic efficiency allows us to produce the actual work required by that pump, right, or the power. So if we just go ahead and rearrange this equation, the actual the actual power, which is what we're looking for, is equal to the ideal power divided by the isentropic efficiency. And if we think about how we could compute the ideal power, we can use the first law of thermodynamics, which states that the heat transfer minus the work is equal to the change in energy of the system. The pump is a open system, so we use enthalpy changes, and we're going to neglect kinetic and potential energy changes. So what we have here is the first law for an open system. And remember that for the isentropic case, that's something that we can easily calculate. Isentropic just means adiabatic and reversible. Adiabatic means zero heat transfer. So the pump power is equal to, actually, let's just do work here. The work is equal to the mass times the enthalpy change. And if we take a time rate of change on both sides, we can see that the power is equal to the mass flow rate times the change in enthalpy. Now, there's an important simplification for pumps, or just devices that increase the pressure of liquids, that the enthalpy change is just the specific volume times the change in pressure. And that comes from a fundamental relationship, which is that TDS is equal to DH minus VDP. For isentropic devices, the DS, there's no change in enthalpy, so that's zero. So enthalpy changes could be computed by this relationship right here. And if we integrate both sides, we can see that the enthalpy change for a liquid, we know that liquids have a special property, they're incompressible. The density is constant. And remember that density is just the inverse of the specific volume, right? Specific volume is just volume per unit mass, and density is mass per unit volume. They're inverses of each other. For incompressible substances like liquids, the specific volume is constant. We could take it out this integration, and we have the integral of dp, which is just delta p. So essentially, to compute the ideal isentropic power, all we need to do is plug into this relationship right here, which is just the mass flow rate times the specific volume times the change in pressure. And we need to divide by the given isentropic efficiency for the pump. And then we would have our solution right here, which is the actual work input required by that pump. Okay, so what kind of things do we have and what are we looking for? We know what the mass flow rate is. We don't know what the specific volume is, and we don't know what the change in pressure is either, but we do know the isentropic efficiency of the pump. So we know the mass flow rate. We don't know the specific volume. We know what the pressure of that pump is at the exit, right? Remember that a constant pressure process is occurring inside of the boiler. So the pressure at 3 is the same thing as the pressure at 2, which is equal to 5.5 megapascals. So I'm just going to label that as P2. Remember that this is the same thing as P3 though, minus the pressure at state point 1. Now, how could we find the pressure at state point 1? We know everything about state point 4 because we know its temperature is 60 degrees C and we know its quality. It's equal to 1 or it's a saturated vapor. So we can go into the steam tables. We can find the specific volume at state point 1, knowing that the pressure is exactly the same as state point 1 and state point 4. So we can find the specific volume of a saturated liquid, which is VF. And we can also find the pressure at state point 4, which is equal to the pressure at state point 1. That's just going to be equal to the saturation pressure at T4. So to summarize what we're going to do in these tables here is we're going to go to T4, which is equal to 60 degrees Celsius. And we're going to go ahead and extract P4, which is equal to P1. That's just the saturation pressure at that 60 degree. And we're also going to extract the specific volume of a saturated liquid, and we're going to use that in our equation over here. Okay, so let's go ahead and grab some of that information. We're going to go ahead to page 172 of the reference. Page 172 of the reference. Is it 172? Sorry, it is 157 here. Page 157 of the reference, you see we have the steam tables here, and we know that at 60 degrees C, we're looking for the saturation pressure, which looks like 19.94 kPa.
Additionally, we're looking for the specific volume of a saturated liquid. That's VF. It's 0.001017. Let's go ahead and log those values. The VF value is 0.001017 cubic meters per kilogram, and the saturation pressure is 19.94 kilopascals. Okay, let's go ahead and plug in these values into our equation here and be able to find our answer. So we know that to find the actual pump power, what we need to do is take our mass flow rate of 42 kilograms per second, multiply it by our specific volume that we just found, 0.001017. Multiply that by the difference in pressure values. We need to have both of those in kPa. And if we want to convert that 5.5 megapascals to kPa, we multiply by 10 to the third. So we have 5.5 times 10 to the third. We're going to go ahead and subtract the saturation pressure that we just found, which is 19.94. And we're going to divide that. We're going to divide this value by 83%. So 0.83. And let's see what the output of this calculation is. 282. And let's check some of our units here. We have kilogram per second. For the mass flow rate, we have cubic meters per kilogram. For the specific volume, we have kilopascal or kilonewton per meter squared. For the pressure, and the efficiency is dimensionless. So the kilograms are going to cancel out. The meter is going to cancel out. We have kilonewton meter per second. A kilonewton meter is a kilojoule. Kilojoule per second is a kilowatt. So this entire thing reduces to kilowatts, and the answer is answer choice D. If we quickly look inside of the reference manual, I'm going to show you some of these equations here that you can find for a pump. The special case here, which is page 149. For a pump, we know that the enthalpy change, the difference between the exit and the entrance, can be computed using the product of the specific volume times the change in pressure. So that's the equation that we use, and we understand fundamentally where that came from, that TDS relationship. And they highlight here the isentropic efficiency equations for a compressor, which is a work input device, just like a pump. And additionally, they highlight the isentropic efficiency for a turbine. So we can kind of find all of this information right here. And there are some other equations related to boilers, but really, if we understand the basic idea of this cycle here, and you want to get a positive value, you just take the enthalpy change of the bigger value minus the smaller value, right? Things with higher temperatures will have higher enthalpies, because enthalpy is a function of temperature, right? And at higher temperatures means higher enthalpies. Okay, let's go ahead and move on to the next problem. In this problem here, we have a gas mixture, which is 40% nitrogen and 60% helium by mass. So those are the given mass fractions denoted by Y. Y of N2 is equal to 40%. Y of helium is 60%, and it expands isentropically. So we know that the change in entropy is equal to zero, or we have a constant entropy. It's expanding in a turbine. So a turbine is an expansion device, and it's going to produce some work output. But at state point 1, the entrance, we have a pressure equal to 6,000 kPa and a temperature at state point 1 equal to 700 degrees Celsius. And it's expanding in that turbine to a pressure at state point 2, which is equal to 300 kilopascals. It says to use room temperature properties and to find the work per unit mass. That is just lowercase w here, and that's what we're looking for. We know that fundamentally, if we're looking for a work term, we want to really focus in on that first law of thermodynamics. And this is for an open system.
For an open system, we know that that change in energy term is replaced by a change in enthalpy plus a change in kinetic plus a change in potential. How do we know it was an open system? We have mass crossing the boundary of the turbine, right? We think about it kind of being the inside walls of the turbine. We constantly have mass into and out of. There's some mass flow rate associated with this. And we know that because mass is crossing the boundary, we have an open system. We're going to be using enthalpy changes. We're not given any speeds, so we're going to neglect kinetic energy changes, and no heights, no dimensions are given. We're going to neglect potential energy changes. And we know that this is an isentropic process. Isentropic means adiabatic and reversible. Adiabatic means zero heat transfer. So fundamentally, right, the work can be computed if we just know what the difference between H1 and H2 is. Right, you can see I moved that negative to the other side. We can also write this as the mass multiplied by H1 minus H2 in terms of the specific enthalpies. And if we move the mass to the other side, we'll have the work per unit mass is just H1 minus H2. If we want to find enthalpy changes, we use Cp delta T. If we want to find internal energy changes, we use Cv. But we're going to use Cp in this case to find that enthalpy change. Now, we have no idea what Cp for this mixture is, right? Remember, we're dealing with an ideal gas mixture here, and we kind of understand what the mass fractions are, but we don't know what the mixture properties are. We know what the temperature is at state point 1, but we don't know what the temperature is at state point 2. For an ideal gas undergoing an isentropic process, there's some relationship between the temperature ratio and the pressure ratio, which we have since we have P1 and P2. So we can use that relationship to be able to find T2. T2 over T1 is equal to P2 over P1 raised to a exponent, which is K minus 1 over K, where K is just the ratio of specific heats. Is called Laplace's coefficient, or the ratio of specific heats. Okay, so this is what we're going to be able to use to find the temperature at state point 2. And you can see on the upper right, I have some important ideas that I want to discuss with you before we go ahead and look where we can find some of this information in the reference. There is Amagat's law of additive volumes. And what that says is that we can take our component volumes, the V1 and V2, and we can sum them together to get the total volumes. Now, these are called component volumes, components of the mixture, or partial volumes. The sum of the partial volumes is equal to the total volume. Additionally, there's Dalton's law of additive pressures. We can take our component pressures or partial pressures of all of the components of the mixture and add them all up to get a total pressure. Now, these ideas are super important when you're looking at gas mixture problems like these, or a special gas mixture that we study, which is an air-water vapor mixture. That topic is called psychrometrics, and it's heavily used in HVAC, and we're going to get problems on that in the FE exam, and we're going to see a problem like that a little bit later. If we think about, if we can sum volumes together to be able to get a total volume, we sum one component plus another component to get a total volume. We can also write this in terms of specific volumes here to get this. And if we move the total mass to the other side, dividing both sides by the mass, you can see that the mass fraction could be used to be able to find mixture properties, mixture specific volumes. And that's true also for CPs, that's true for CVs. And that's something that we need in this problem, right? We need to be able to find the mixture CP, the mixture CV, so that we can find the ratio of specific heats. Once we find that ratio of specific heats, we're able to find the final temperature, the temperature exiting the turbine. Once we know the temperature exiting the turbine, we'd be able to find this delta T over here. And knowing that Cp that we previously calculated when we're doing the K, then we'd be able to find our work per unit mass. So we went over Amagat's law, Dalton's law. We looked at volume as an example to emphasize why we can use mass fractions to be able to find mixture properties. and we looked at that ideal gas relationship. Let me show you these things inside of the FE reference manual here. Okay, so the first thing is that for ideal gases, what you can see is that if you have an isentropic process, there is a relationship between the temperature ratio and the pressure ratio, and they're related via this exponent here, which is the ratio of specific heats. This is heavily used when you're looking at air standard cycles, cold air standard cycles, as well as a compressible flow. Now for ideal gas mixtures, we know that mass fractions are used a lot, as well as mole fractions. And we kind of reviewed the idea of Dalton's law, of Amagat's law, which are these two lines right here. Summing the partial volumes, you get the total volume. Summing the partial pressures, you get the total pressure. And mass fractions are important to be able to find some of these mixture properties. So let's go ahead and find the mixture Cp and Cv, and let's use that value to find the ratio of specific heats K that will plug into the isentropic relationship. And finally, we'll plug into Cp delta T to be able to find our work per unit mass. Let's get some of those properties here for nitrogen and for helium, checking the end of the thermodynamics section here. All right, so for gases, I'm seeing some Cp and Cv data, and they said that it is appropriate to be able to use room temperature properties here. So I'm looking at helium, I'm also looking at nitrogen, and I'm going to highlight the Cp values, Cp as well as the Cv values. Okay, so these are the values that we're going to use along with the mass fractions to be able to find the mixture properties. Let's go ahead and log some of this data. Okay, so Cp for the mixture is equal to the mass fraction of nitrogen multiplied by the Cp of the nitrogen plus the mass fraction of the helium multiplied by Cp of the helium. I go ahead and plug into the equation right here. Cp of the mixture is the mass fraction of nitrogen was 40%. This right here. Cp of N2, that's 1.04, plus the mass fraction of helium is 60%. Cp of helium is equal to 5.19. So the Cp of the mixture turns out to be 3.53 kilojoules per kilogram Kelvin. So that's Cp of the mixture. Cv of the mixture could be also computed. It's just that 40% multiplied by Cv for nitrogen. Cv for nitrogen is 0.743 plus 60% multiplied by Cv for helium, which is 3.12. And we see a value here of 2.1692. Okay, that's kilojoules per kilogram Kelvin. If we go ahead and take that ratio, we get 1.63 approximately. Okay, Cp over Cv is 1.63. And we can go ahead and plug it into this relationship right here. 1.63 minus 1 divided by 1.63 gives us a value of 0.385. Let's go ahead and plug in that pressure ratio. Let me go ahead and remove some of this information here so it's a little bit, have some space to write. All right. T2 is equal to T1. T1 is, we'll plug in just now. I know what that ratio of pressure is. The pressure at state point 2 is 300 kPa. Pressure at state point 1 is 6,000 kPa. That's a 1/20th ratio raised to the, when we plug in that 1.63 minus 1 over 1.63, and I plug in my T100 as 700 degrees C plus 273.15. Note that the temperature must be in Kelvin here. What you get for T2 is 306.65 Kelvin. We can go ahead and plug into our work per unit mass relationship here, which is the fact that Cp of the mixture multiplied by T1 minus T2 is going to be our work per unit mass. Cp of the mixture, we got 3.53. T1 was equal to 700 plus 273.15. And the temperature at state point 2 is 306.65. If we plug in, what we get is 2352 kilojoules per kilogram. Looks like answer choice B here. In this problem here, we're really focused on the idea of psychrometrics, which is just a fancy way of saying the study of air, water, vapor mixtures, and we have an HVAC process that we're going to be looking at inside of this problem. So we have atmospheric air that's entering a cooling system at 35 degrees Celsius. Let's call that state point 1, 35 degrees Celsius, and a pressure equal to 100 kilopascals. Now, as it's cooled, water vapor is observed to condense out of the air at 27.5 degrees Celsius. 27.5 degrees Celsius is kind of the endpoint of our process here. And we're looking for the humidity ratio, which also is called the absolute humidity or specific humidity. And we're also looking for the relative humidity of the incoming air. So that is omega 1 and phi 1. And what I'm going to do is quickly define these terms for you to review the idea of specific humidity or the humidity ratio. Omega 1, or omega in general, is just the mass of the water vapor per unit mass of the dry air. And if we kind of substitute in the ideal gas equation of state, as well as apply Avogadro's and Dalton's law, what we end up getting is that this is equivalent to the pressure ratio, PV over PA, multiplied by the ratio of the gas constants, RA over RV. And this RA over RV turns out to be around 0.622. So it's essentially 0.622 PV divided by, and they substitute in for the partial pressure of the dry air. Remember the relationship that the total pressure is just the sum of the component pressures, the water vapor and the dry air components. So we can see that in the denominator, if we just want to write this as a function of the partial pressure of the water vapor, we can plug in the relationship that I wrote down on the left-hand side. So you see that omega is really just a function of the partial pressure of the water vapor, and the total pressure usually doesn't change in these systems, right? It's 100 kilopascals at the first state. It remains that at the second state. That's why I just label this as P. Okay, if we think a little bit about some important things that were said inside of the problem, it says water vapor is observed to condense out of the air at 27.5 degrees C. At that point, the only point where you would see water vapor condensing out of air is when it's fully saturated. And that's kind of taken up by this phi parameter. Phi is the mass of the water vapor divided by the maximum amount of water vapor that could be held in the air at that point. That's usually denoted by this subscript G. That's just could be reduced if we plug in the ideal gas equation of state. The ideal gas equation of state, the partial pressure of the water vapor divided by the maximum amount of water vapor that could be held in the air at that point, turns out to be just this pressure ratio. The top is the partial pressure of the water vapor. The bottom is essentially the saturation pressure. This is just P sat at whatever temperature that you're looking at. Okay, so this is the relative humidity, and for state point 2, we really have a fully saturated state, right? And that means that phi is equal to 1. And if phi is equal to 1, that means that the partial pressure of the water vapor at state point 2 is equal to Pg at state point 2. That's just the saturation pressure at a temperature which is equal to 27.5 degrees Celsius. So we know that we can easily find that information. So we'd be able to find PV2 pretty easily. Now, how could that help us? If we observe the process that's going on, going from state point 1 to state point 2, we know that the mass of the water vapor is going to be the same. The mass of the dry air is going to be same. So that means omega is actually constant for this process. Omega 2 is equal to omega 1. And if we know what the partial pressure of the water vapor is, then we'd be able to easily find omega 2, and we can find omega 1. That's what we're looking for in this problem. Okay, so if omega is constant, and if omega is constant during the process, we know omega is only a function of the partial pressure of the water vapor. The total pressure is unchanged. So that means that we have constant omega. That means PV1 is equal to PV2. Let's go ahead and write that down. Note that PV1 is equal to PV2. Okay. So let's go ahead and quickly find this omega value. That's just equal to 0.622 multiplied by PV. Now we can easily find that PV2 value is the same as PV1 divided by the given P minus PV2. Let's go ahead and compute this value here. All we need to do is find the saturation pressure at a temperature of 27.5 degrees C. Let's go into the steam tables and find that value. So right here, I'm at the water tables, and you see I have highlighted here 25 degrees C and 25 degrees C and 30 degrees C, and that's because that's bounding the temperature of interest for me, that 27.5. I know that it's that 27.5 is directly in the center of 25 and 30. And if I'm looking for the saturation pressure associated with 27.5, I could just take the average of these two values to be able to find that saturation pressure. So let's go ahead and perform that average so that we can find the saturation pressure associated with 27.5 degrees. That is just, let me pull it up on the other screen here. (3.169) plus 4.246 over 2 divided by the total pressure is just 100 minus the same average value, 3.169 plus 4.246 divided by 2. Let's go ahead and plug this in, see if we can find what the omega of state point 2, and that's just the same thing as the omega of state point 1. Okay, the average value is around 3.7075. So I'm going to take that average value divided by 100 minus the average and multiply by 0.622 to get a omega at state point 2. That's the same thing as the omega at state point 1, equal to 0.024 here. And that is kilograms of water vapor per kilograms of dry air. And it's definitely beneficial to be able to write down your units in terms of water vapor and dry air, because they cancel out really nicely and help to keep everything organized. So the first thing that I'm looking at is we have that's the omega value is 0.024. So I've narrowed it down to choice A or C. Now I just need to find the phi at state point 1. Remember that the partial pressure of the water vapor is constant during this process. So we know what the partial pressure of the water vapor is. That's kind of this average value that we just found over here. It turned out to be 3.7075. This was just the average, kind of this calculation right here. Let me circulate for you guys. Okay, so now we have what that partial pressure of the water vapor is at state point 1 divided by PG at state point 1. That's just P sat associated with 35 degrees C. Let's go ahead and look at the P sat associated with 35 degrees C real quick. And we can see that P sat associated with 35 degrees C is just 5.628. We can quickly write that down, 5.628, to get this ratio equal to 0.658. And there is no units associated with that, right? It's both of them are water vapor, so no units associated with that. We see the answer choice is A, and I'm going to show you guys how quickly you can solve this problem using the psychrometric chart. I think that it's really important in terms of understanding the process to be able to apply these equations and to understand the idea of simple heating and simple cooling. But you can much faster, much more quickly complete this problem if you use a psychrometric table, right? And that's kind of the benefit of that psych chart. Okay, we're going to the end of the thermodynamics section, and you can see here that I have a psych chart. Now, if we think about what was the fully defined state that we had that state point 2. It was at 27.5 degrees, which is around here, and it was fully saturated. And lines of relative humidity are represented by these kind of curved lines here. This would represent 100%. Relative humidity, you could see they're marked off here, 90, 80, 70% relative humidity. So the intersection of my 27.5 degrees and my line of relative humidity is this state point 2 right here. I'm going to draw that in a different color. Looks right around here. And this is at state point 2. And we know a constant omega process is occurring from state point 1 to state point 2. And I know what the temperature is at state point 1 is 35 degrees Celsius. Now, this temperature down here is the dry bulb temperature, which is just the temperature you measure on a normal thermometer. That's the temperature that was given. This y-axis over here is omega, which is the specific or relative humidity, the specific humidity or the humidity ratio or the absolute humidity. And we understand that, these kind of arcing upward lines are the relative humidity values. So if we go up at the intersection of the omega as well as the 35 degrees C, we see that state point 1 could be fixed right here. State point 1 here, and we travel from state point 1 to state point 2 in a constant omega process. So you can see that the omega at state point 1 is pretty close to 0.024. And the variation that we see is because this chart is technically made for a pressure of 101.325. We had a total pressure in our problem of 100, right? So there's a little bit of delta between the values, but approximately omega is 0.024. And then what about for the lines of relative humidity? You can see that we're between the lines of 60 and 70 over here. So we'd be able to fully solve the problem, right? The tricky part of this problem was really understanding the idea of the simple cooling process that was occurring at a constant omega, right? The mass of the water vapor is unchanged. The mass of the dry air is unchanged. So going from state point 1 to state point 2, we have a horizontal or constant omega process. The last thing I want to discuss with you guys here is where you can find some of those relevant equations that we were looking at relating to psychrometrics. And you can find that on page 150 of the reference manual here. We see where the specific humidity and the different names are called out in the reference manual. And fundamentally, it's just the mass of the water vapor per unit mass of the dry air. You can see that alternate form of omega, which is just a function of the partial pressure of the water vapor, or alternatively, this kind of ratio between the water vapor and dry air, partial pressures. And you can see the relative humidity definition and what PG is. Okay, let's go ahead and move on to the next problem. Let's move into this final problem where we're really going to be focused on reviewing the fundamental ideas of combustion and combustion products. It says during a combustion process, hexane fuel, which is C6H14, so it's a hydrocarbon fuel, it burns with 100% excess air. Additionally, the molar mass of air and hexane are shown above. The air to fuel ratio is most nearly. Okay. Essentially, what we're looking for in this problem is that air to fuel ratio. And we know that we're not dealing with just stoichiometric combustion. What we have is 100% excess air. And I'll explain exactly what that means. Essentially, the air to fuel ratio is exactly as it sounds. It's the mass of air divided by the mass of fuel. Now, we can find the mass of air by taking the number of moles of air multiplying the molar mass of air. If you look at the units here, it makes sense that we're using that kind of formula here. number of moles is like kilomoles, and the molar mass is kilograms per kilomole. So the kilomoles cross out, we're left with kilograms. That equation makes sense. And the number of moles of fuel divided by the molar mass of fuel. Okay, so that means if we're able to find this correct number of moles of air to number of moles of fuel, we already have the molar mass of air and the molar mass of fuel. We'd be able to find our answer. How we find that molar ratio that we need is by looking at the stoichiometric combustion equation and then incorporating the excess air afterwards. If we write down exactly what the combustion equation is, for hexane, we have some amount of fuel, C6H14, is burned with some amount of air. Now, air is just oxygen plus 3.76 nitrogen. Now, why is it like that exactly? Air is 21% oxygen and 79% nitrogen. Someone didn't like working with these decimals here, so they multiply by 1 over 0.21 here. And if you multiply that ratio, then you get what you see above, right? The 1 plus 3.76 and 2. Okay, what that's going to produce is some amount of carbon dioxide, some amount of water vapor, and some amount of unburnt nitrogen. This is for the stoichiometric combustion equation, so theoretically, this is the amount of air we need. If we wanted to modify this to allow for some amount of excess air, then all we do is multiply this by a factor, 1 plus the excess air fraction. We multiply that by the amount of air that we have, and we'd gain a term on the right-hand side, which would be some amount of unburnt oxygen, that excess oxygen term. Okay, so in terms of what we need to do, we need to take the number of moles of air, which is 1 plus the excess air fraction, multiplied by our stoichiometric coefficient. We're going to take that and multiply it by 4.76. The 4.76 is there because we have 4.76 moles of air. There's 1 mole of oxygen and 3.76 moles of nitrogen. So overall, that's 4.76 moles of air. And we have those two factors in front. We take that, which is the number of moles of air, multiplied by the molar mass of air, which is 29. It's in the givens here. We take that value and divide it by the number of moles of fuel. We're going to assume we have 1 mole of fuel here. So this is just a 1 here. And the molar mass of fuel is just 86.177. So if we can find our stoichiometric coefficient here, we know what our excess air fraction is, just 1, right? 100% or 1. So all we need to do is solve for that stoichiometric coefficient. And we do that by looking at the combustion equation without any excess air. So I'm going to go ahead and remove that excess air. And we're just going to solve this just doing stoichiometry. So we're going to start with the carbon balance. We have 6 carbons on the left side. And how many carbons do we have on the right side? We have 8 carbons on the right side. So immediately we know that that coefficient A is equal to 6. What about the amount of hydrogens, the amount of H's that we have? What we see is that we have 14 hydrogens on the left-hand side. What about the right-hand side? We can go through and count it. We have 2B amounts of hydrogens on the right-hand side. So that means B is equal to 7. And what about oxygen? Oh, how many oxygens do we have? We have 2 times the stoichiometric coefficient. That is the amount of O's on the left-hand side. What about on the right-hand side? We have 2A plus B. Now we know what A is and we know what B is since we just performed our stoichiometry. A was 6, B is 7. And we can solve for our stoichiometric coefficient here, which is 12 plus 7 divided by 2. That's 19 over 2. If we go ahead and plug in that 19 over 2 value here as our stoichiometric coefficient, we see that 19 over 2 and this 2 from the 1 plus excess air fraction is going to cancel. We have a 19 times 4.76 multiplied by 29 divided by 86.177. The units on that is kilograms of air per kilograms of fuel. And it turns out to be around 30.43. Okay, so this is the answer. Let's go ahead and check that answer. 30.43.
Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top 3 subjects, what are my bottom 3 subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $9.99. Let's get back into the video. If you made it this far in the review, I just want to say thank you for watching the video. The next review I'll be releasing is the mechanics and material review, so I hope to see you there. If you enjoyed the video, consider leaving a like and subscribing for more content like this. I hope to see you in the next one. Goodbye.